In this video, I'm going to talk about how to find the distance between a point and a plane in R3. In this first part of the video, I'm going to go through a more standard approach that sort of breaks down the logic behind the scenes. And I'll just start by, looking at an example. So first of all, every time you see a plane equation, you'll have to identify the normal vector, which is simply just the coefficients of the x, y, and z in the plane equation. So the normal vector is here 3, 1, and -4. So I can fill in the blank over here, 3, 1, -4. And now the second step would be, so the point here, Q, is the point of interest. So 2, 1, and 2. But like right now, I don't know what P is, but we can use this equation to identify, well, like P is just a random point, right? So we can simply just see, or like plug a number in. I'll just say, so 1, 0, -1. If you plug this in the equation, it would, it would satisfy this equation. Means that P is on the plane. Okay? So what is PQ? The vector from point P to point Q is simply the first component of Q minus the first component of P, which is 1, 1, and then do the same thing on the third one. 2 minus -1 is 3. Now we get this vector, which is 1, 1, 3. But how do we find the distance between that point of interest Q and the plane? All we gotta do is just do a projection. The vector PQ onto the normal vector N. So the distance of proj of PQ onto N would be what we're looking for. So just imagine there's like a light over here that kind of shines in this direction. And then now we can see that actually it projects. This is the projection of that. And like this would be parallel to this. I mean, these two are the exact same, right? So we get the distance, which is the projection of PQ onto the normal vector. Like you can actually move the normal vector around. So if I move it down the N down here, I would still get the same projection, which is the proj of PQ onto N. So how do we calculate this? So there's actually one formula for this one. Well, since like this is all in the absolute value, which is denoting its distance. So inside of the absolute value is the projection. And then here's a little tip for you. Whatever's on the bottom, you see it 4 times. What I mean by that is, so PQ dot product with N. This is the first time, 2 times, times N. that is the formula for projection. And here, all we gotta do is just plug in the numbers. So what is PQ? PQ is 1, 1, 3, dotted with, what is N? 3, 1, negative 4. And what is N squared? 3, 1, negative 4, all squared, times N, 3, 1, negative 4. So now I get 1 times 3 equals 3, 3 plus 1 equals 4, 4 minus 12 equals negative 8. And on the denominator, it'll be 26, which cancels out to 13 and then 4. Like that. So I can actually factor this out since it's all in the absolute value. I can just basically factor this out, and then so the negative sign doesn't matter because it's just a scalar, like that. And then I get, so this would be your final answer. However, in this shortcut, all we gotta do is simply, so the plane is 3x plus 4, 3x plus y minus 4z equals 7. All we gotta do is to write it in a form that the right-hand side of the equation is 0. And we plug in the point of interest, which is, in this case, 2, 1, 2. So, and then we put it in the absolute value. So 3 times the point is Q212. 3 times 2 plus 1 minus 8 minus 7 all over, and then I divide by the square root of the sum of the coefficients squared, which means, in this case, 3 squared plus 1 squared plus negative 4 squared. This is equal to 6 plus 1 equals 7, 7 minus 7 equals 0, negative 8, so it's 8. And then here it's square root of 26. And this is exactly the same as this one. Well, I can simply do it like 4 times square root of 2 times square root of 13. Denominator, square root of 13, square root of 13. Like that. And then I multiply square root of 2 on both sides. So I indeed get square root of 26, and 8.